morning. Here we are at the physics video lecture once again. Physics 105A video lecture 11. Today we want to do a little bit of review. There's a homework problem people were interested in seeing done, and we'll start with that, and then I have a couple of other interesting topics as well. But let's begin with this problem here where we take the conservation of energy, separate variables, find the time as a function of position, and we're going to let u of x equal mgx. So this is just the vertical freefall problem, and we know what the answer is supposed to be. So the separation of variables we've done a few times here leads to t equals integral x0 to x dx prime root 2 over m e minus u, and so we're going to write e minus mgx prime like that. And now we have to do this integration. We have, I'll pull out the 1 over root 2 over m right away. And then the antiderivative of the square root of e minus mgx would be the square root of e minus mgx. But when we take the derivative, of course, we get the 1/2, so we're going to have a 2 up here. And then the inner derivative, we're going to have minus mg. So this from x0 to x is what we have to evaluate. And it's these little algebraic shenanigans that can lead us into trouble. So let's see if we can pull this off with this factor here. Looks like we have a root 2 and these cancel here, and this will go in there as an m, and the g will be outside. Okay, root 2, and we'll have a minus sign. So 2 over 2, root 2, bring that in, m squared, m root m, and the g's outside. Good. So this should work. Now we're going to evaluate this at x and at x0. So we have root e minus mgx minus the square root of e minus mgx0. And before I go on, notice that there's what we're solving for in the final analysis. What's under this square root is actually a constant, because energy is a constant and x0 is a constant. Okay. So what I'm going to do next is just cross multiply this over to the t, and then I'll square. So we're going to have minus gt and then root m over 2, and then this same thing here, e minus mgx minus root e minus mgx0. So this thing we now have to somehow square. And because this is a constant, I'm going to bring this over to the other side and combine it with this, and then square both sides. One more thing I should actually put in here. We have plus or minus right here. So we actually have plus or minus all the way here. And this, therefore, we could have minus or plus right there. And if we carry that through over here, we will have a minus or plus right here. Okay, I'm going to leave it just with the sign that we had, but just take note that we had that there, and you'll see right where that comes into play. Okay, so let's do this. What we're going to write is root e minus mgx equals root e minus mgx naught minus gt root m over 2. And now we're going to square both sides. And we get e minus mgx equals e minus mgx 0. Those e's are going to go away, but we're going to get cross terms now. So minus 2 root e minus mgx 0 gt root m over 2, right? That looks like a mess. And then plus gt g squared t squared m over 2. So now the last step is to divide. Well, first we'll go ahead and get rid of these. And we can divide by negative mg. This was minus, okay, negative mg and negative mg, and see what happens. Let's start over here. G squared going to go away there, m cancels, so yes, sure enough, this one gives us our minus gt squared over 2. Over here we have x equals x0, so it's this thing here that we're interested in, because that just does not look friendly, right? So let's see what we have there. I'm going to do this. Equals b0t. We'll put a little question mark here. That's what we're supposed to get, right? We're supposed to get b0t. We know that x0, b0t minus 2t squared. So yeah, this thing could be better, could be worse. Let's see what we have here. The minus signs are going to cancel. I'll say something about that later on as well. So let's see what we have here. We have gt, minus signs have already gone away. We have gt root m over m, got a 2 and a 2. So we've got the root 2, m over m, we've got the root m, 2 over root 2. And we have a g right here as well. Actually, so the g canceled. Okay, so let's work on this here. We have g was gone, root 2 over m. Good. So we got the t there, root e minus mg x0. Maybe the best way to deal with this now is to ask, is root 2 over m root e minus mg x naught, is this equal to b0? Okay. And actually we can see what's going on now. So we're postulating this is our v sub 0, and if I cross multiply this over to there and square, here's what we find. okay, we find E minus mgx0 is equal to mv0 squared over 2, right? So finally, what we're just saying is E is mgx0 plus mv0 squared over 2. Check, because that's just saying the energy is the sum of the initial potential energy plus the initial kinetic energy. Okay, so that's a pretty fiddly problem, but you'll see if you take it through from beginning to end like we did right here, there's a fair amount of insight to be gained, and so that's why it's a very worthwhile problem. Of course, this answer we've already discovered by other methods as well. Okay, but there you have it. We therefore have our x equals x0 plus mu0 t minus a half gt squared. Free fall, and because it's the constant force, constant acceleration problem, it's very important. We've already seen limiting cases always end up with that thing. Good, let's consult the clock. Very well. So yeah, this is worth, putting down in really clear form in your notes, because there's a lot going on here. So let's go ahead and tackle our next project. Yeah, I'll erase all of this. So we're going to come back to the discussion of the potential energy and the force and a couple of connections that exist there. Okay, I had mentioned the fundamental theorem of calculus some time ago. So what are we going to call this? Potential energy. We'll just call this potential energy. And force. So we introduced the potential energy in this integral form, minus integral some constant to x, and we integrate over x prime. So x prime is just an integration variable. This function of x has its argument up there. So that's how we introduced it. And then we say, okay, du dx, or u prime of x, is equal to minus f of x. So that's a theorem in mathematics that I want to remind us of. It's a good proof. So I'll just prove it for the general case. Prove. You've seen this before in your math class, I'm sure, because of the fundamental theorem of calculus. Let's just remind ourselves. So begin with, so let f of x equal the integral f of x prime dx prime from a to x. And now we want to just, without the minus sign, but I'm just talking, so this is not that force, this is just a function and its antiderivative, okay? I just want to show you the proof of this again. Then f prime of x, what we're going to do is apply the definition of the derivative. So that's the limit as h goes to 0 of, we'll do every step here, of 1 over h f of x plus h minus f of x. All right, so that's the definition of the derivative. And let's go ahead and plug in our function there. Equals the limit as h goes to 0 of 1 over h. And now we'll plug in this integral. So we'll have a to x plus h f of x prime dx prime minus integral a to x. I'm just being literal about what I'm plugging in. Is the x plus h. There's the x. But then limit h goes to 0. Yeah, but what's left, the difference of these two integrals is just the difference from x to x plus h. In fact, let's draw a little picture here. We've got x, let's call that x, let's call that x plus h. And a could be somewhere down here. So we have the area under the curve, but when we take the difference of those two, it's just one I'm gonna draw in a little darker, okay? So that's the integral that we're talking about. So when we have your integral x plus h x prime dx prime. Good, is that all still visible? Visible enough. So that's what we're looking at. And now, a little bit hidden. But the point is, when h goes to 0, this little area here itself goes to 0. So we have limit h goes to 0, 1 over h, and this integral itself can be expressed as h times f of, I'm just going to use a x sub 0. Well, I'm going to use a Greek letter C. Okay. Where our letter C here is an element of x plus h, of that little interval. And of course that interval is being squeezed down to nothing, to x. At this point, these things have canceled, and there you have it. So that's your proof of this relation here. So the derivative of that expression integrated to the upper bound is just the integrand evaluated at the upper bound. If you're interested, you can have x as the lower bound, and then you'll actually get this theorem with a minus sign in front of it. Okay, you can add that to your arsenal as well. But yeah, so this is what we have, and therefore when we have a potential energy function, we have u prime of x is equal to minus, because we defined it with a minus sign, equal to minus the force that we use to generate that expression. Okay, so that's just a useful fact to have. Now, once more, I'm going to consult the clock. Okay, so now let's talk about potential energy functions and their Taylor expansion. Okay, so next, potential energy and Taylor expansion. In the case that we're talking about now, it's the potential energy with a local minimum, because what we did was we expanded it and found a certain interesting thing. So let's go ahead and write this. We had some function with a local minimum, and x0 marks that local minimum. And we had expanded it in Taylor expansion, where we said, okay, u of x0 plus u prime of x0, x minus x0. Go ahead and free up some board here. Plus 1/2 u double prime x minus x0 squared, plus and so on. And we can always eliminate the constant. The force is going to determine the mass times acceleration, Newton's law, and the force is a derivative of the potential energy. So you have a constant, you take a derivative of it at 0. Okay. So potential energies are arbitrarily defined within a constant. Since we're at a local minimum, that's 0, and so this is the first non-trivial term. So now let's just, without giving it a new name, u of x be this 1/2 u double prime of x0 x minus x0 squared. And this is, of course, a constant, and I said we could replace it with the letter k if we want to. Under many circumstances we do. Okay. And again, this is just the parabola that nests with the curve there. So for sufficiently small x minus x0, you take a small interval, then you consider this to be as accurate as you want. Okay. So now the question is, what is the force? Force, question mark. And we're just going to take the derivative. F equals a minus sign here, right? Minus u prime of x, because f is a function of x. So we have minus, we have 1/2 u double prime of x0, and there's our x. Okay, this was all constants, and the derivative of that, of course, is 2 times x minus x0. 2 times x minus x0. So when all is said and done, f of x is equal to minus u double prime of x0 x minus x0, or minus k x minus x0. So there you're recognizing Hooke's law. Okay. And then I'm just, there's our definition. K is u double prime. There you're recognizing Hooke's law, that linear force law, and it's x minus x0 because x0 is the point of equilibrium. Okay, this is important to understand because I've seen a lot of errors made when it comes to actually differentiating this thing. What people will often do is forget that this u second derivative, this is a constant now. When we did the expansion, these are constants and the argument x is explicitly here and here. Okay? And this constant we just threw away. Okay, so now we're back to solving Newton's law, and this will bring us full circle. So now we're back to Newton's law. We're continuing this expression here. Newton's law, we have, I'll even write it this way, mx second derivative equals f. And of course these were functions that were just a function of position. Mx double dot equals minus k x minus x0. So now we're doing the motion in that little red interval there, in this original potential well. Now let x minus, here, let y equal, I'm just choosing another letter, choose anything I want. Y equal x minus x0. Y dot is x dot. Y double dot is x double dot. Okay. So with that substitution, what can I have? My double dot is equal to minus k times y, just another letter. And of course, this is what we solved. What we have already solved. So we've solved this before. I'll even put a note here. This was u equals 1/2 k y squared. We did the whole quadrature for that. And so since we have this differential equation and we know its solution, we can just write y is equal to a cos omega t plus alpha. Omega is equal to root k over m. And you know what this substitution did, we can bring the substitution back, as a matter of fact. Now that we have that solution, we'll wrap it up with this. And x is equal to x0, right? Because y is just x minus x0. So x is equal to x0 plus a cos omega t plus alpha. So we've just shifted, we just have harmonic oscillations, and they've been shifted to happen around x0, which of course makes total sense because that's that parabolic potential right around x0. Once you have solved this a couple times, it suffices to see a differential equation that looks like this to just go immediately to the answer. You're allowed to do that. Once you have this form of a differential equation, doesn't matter what these letters are named, once you have this form, then boom, you have that answer there. So yeah, we're going to be studying harmonic oscillations now, and we've derived them a couple different ways, that's fine. So this will be let's check the clock. I think this is a good place. yeah, we're just gonna stop here today. So in terms of what we have on the notes, make sure you can do everything we did today, okay? It's a shorter lecture, but if you can repeat all these calculations, really understand every step, then you'll be in good shape. And so put those in your lecture notes. Like I always say, make the lecture notes really broad and well spaced out, and you can fill in all manner of little commentary that way. Good, see you guys next time.